All right, we're going to use Ampere's law to find the magnetic field due to a long straight wire, but the wire has an actual radius r. We're going to find the magnetic field inside of the wire and then also outside. And the wire is carrying a uniform current that is coming out of the plane of the page. So in applying Ampere's law is along a closed curve. I add up the magnetic field component that is parallel to the curve, and that has got to equal our permeability of free space, mu naught, times how much current is inside of my closed curve. The first case I'm going to look at is outside of the wire. So for little r bigger than the radius of the wire, so I'm talking about for a loop like this one. So there's my loop gamma that I'm going to apply Ampere's law to, and this loop has some radius little r, unspecified, but it has to be bigger than the radius of the wire. So applying Ampere's law on the left hand side, I'm going to add up all the magnetic field components along my loop. Well, it's a circle, shares the same symmetry as the wire. So this is just on the left hand side going to be the magnitude of the magnetic field times 2 pi r. The magnetic field strength can vary along my curve, and that is just going to be mu naught times how much current is enclosed. Well, all the current's enclosed. It's all inside the wire. And this tells me magnetic field as a function of distance away from my long straight wire is going to be mu naught times I over 2 pi r, which we already knew, but that's where it's coming from. Other case is if we look inside the wire to see what the magnetic field looks like. So for a loop where little r is inside or the same size as the wire. So now I'm going to consider a loop all inside, so something like that. There's little r. And now we're going to use that loop gamma. Now again, my loop that I'm evaluating Ampere's law along is the same symmetry as the wire. So the magnetic field is going to be constant along the loop, and it can't change its orientation. So the left-hand side of Ampere's law is still nice and simple, just going to be B times the circumference of the loop. But on the right-hand side, I don't enclose all of the current. So if that current is uniform, I need to account for how much is inside my loop gamma. Well, it's going to be the ratio of the areas. So the area of my loop gamma divided by the cross-sectional area for the whole wire. And the pi's are going to cancel out. And I can also cancel out 1 power of the radius. to the magnetic field inside the wire. Mu naught times I have 1 power of little r, and in the denominator I have 2 pi radius of the wire squared. So if we think about a plot of what the magnitude of the magnetic field is, where that's where we run out of wire, the magnetic field is going to be uniform. The magnetic field is going to be a linear function of radius until I hit the radius of the wire, a capital R, and then it's going to fall off as 1 over radius. Because outside the wire, the magnetic field of a long straight wire falls off as 1 over R. So inside the wire, at the very center of the wire, there is no magnetic field. As I move further and further away from the center, I'm enclosing more and more of the current. So the magnetic field gets stronger and stronger linearly with distance until I run out of wire. Then when I'm outside of the wire, magnetic field strength is going to fall off as 1 over the distance.